Good morning, students. Myself Vaidegi, working as assistant professor in Sri Muthukumaran Institute of Technology. Today the video lecture is from the subject Analog IC Design for 6th semester ECE student. In this lecture, we will see about the single stage amplifiers in analog IC design, focusing on differential amplifiers with the active loads, cascode and folded cascode configurations. These are fundamental building blocks in analog circuits, and understanding them is key to designing the high performance ICs. First, we see about the introduction to the single stage amplifiers. Single stage amplifiers are the simplest form of amplifiers. Why do we use them? Because they offer simplicity, speed, and reduced phase delay, making them ideal for high frequency applications. They provide high gain with minimal components, superior bandwidth, excellent linearity, and optimized power consumption. In short, they are re-efficient and reliable. Differential amplifier with first we see about the differential amplifier with the active load. The differential amplifier is crucial because it rejects common mode noise signals, giving us a high CMRR. Instead of using a passive resistor, we use a current mirror as the active load. This dramatically increases gain and output impedance. For example, with a resistive load, gain is around 20 dB, but with a PMOS active load, we can achieve 40 to 60 dB. That's a huge performance boost. Next, we see about the performance characteristics. Of course, there are some trade-offs is there. Gain is limited by transistor output resistance and the load impedance. In 180 nanometer CMOS, we can achieve about 60 dB open loop gain. But we must balance gain with output swing and consider linearity, especially in operational amplifiers. In cascode configuration, the cascode configuration. Cascode amplifier. This topology stacks a common gate transistor on top of a common source transistor. What are the benefits? It boosts output impedance, which increases voltage gain. Second, it reaches the Miller effect, improving bandwidth and stability. And third, it enhances gain, typically 2 to 3 times higher than a simple differential pair with active load. Next, we see about the cascode amplifier. But cascode amplifiers are not perfect. The stacked transistors reduce output voltage swing and voltage headroom is lost. Biasing becomes more complex and power consumption increases. So, cascodes are best used in high frequency, high gain applications where the gain bandwidth product is critical and supply voltage is sufficient. Next, we see about the folded cascode amplifier. The folded cascode is an elegant solution for modern low voltage designs. Here, the signal current path folds, separating input and output domains. This allows a wider input common mode range and better output swing compared to telescopic cascodes. This makes it ideal for a low voltage CMOS designs. Next, we see about the folded cascode performance metrics. Let's look at the performance. In 65 nm, CMOS folded cascodes can achieve DC gain up to 110 dB. In 130 nm CMOS, the bandwidth of 2.5 GHz are possible with a stable phase margin of 60 degree. For example, a 0.13 micrometer CMOS design achieved 62.7 dB gain, 133 MHz unity gain bandwidth and consumed only 0.3 milliwatts. Clearly, folded cascodes outperform telescopic designs in output swing. Next, we see about the design enhancement and practical considerations. To push performance further, designers use techniques like gain boosting, adding auxiliary amplifiers to increase DC gain without hurting bandwidth. Common mode feedback circuits stabilize the output voltage. The layout optimization reduces parasitics and mismatch. And with the technology scaling, we must carefully manage short channel effects and reduced supply voltages. Finally, we came to the summary. So, to summarize, differential amplifiers with active loads form the foundation for high gain designs. Cascade amplifiers gain, boost gain, and bandwidth but require careful headroom management. Folded cascades balance gain, swing, and input range, making them ideal for modern low voltage ICs. Always remember, amplifier design is about trade offs. Gain, bandwidth, power, and voltage headroom must all be considered. These topologies remain essential in analog and mixed signal IC design, enabling high performance applications across today's semiconductor technologies. Thank you.